graph the piecewise function in question 7. Okay, so to graph piecewise defined functions, you just have to graph each individual function on a given domain restriction. So where x is 0, that's kind of a separation for us. So basically, on where x is less than or equal to 0, I'm going to graph y equals 5x plus 6. And when x is greater than 0, I'm going to graph y equals x squared plus 2. So the boundary x equals 0 just tells me where to stop graphing one function and start graphing the other. So let's give it a try. 5x plus 6 is a line. It has a y-intercept of positive 6, and I'm going to graph that as a solid circle. The reason being, it's defined where x is greater than or equal to 0, so this is included here. Now, the slope of this line is 5, which means normally I would go up 5 and over 1 because my rise over my run, but that would take me into the next function's bounds. But you can always do the opposite. So I could also go down 5 and back 1. That's what I'll do. So 1, 2, 3, 4, 5, and back 1. There's another point. 1, 2, 3, 4, 5, and back 1. There's another point. 2, 3, 4, 5, and back 1. And that's enough to get a picture of what this line looks like. Okay. I'm going to get rid of these dots. Oh boy, I just got rid of the whole line basically. All right. There, that's fine. Okay, now the next thing that I'm going to do is graph the other equation, which is x squared plus 2. So x squared plus 2 is a parabola that is facing upward, and it's been shifted up 2 units. So I'm just using my translations that we learned earlier in this class. So the vertex is shifted up 2 units. That's where the vertex is going to be. And you know, I could just kind of grab a couple more points, but it really doesn't matter how accurate you're being over here, just as long as you know it's known that you're drawing a parabola. That's all there is to it. Just graph one function on one side of the boundary, the other function on the other side of the boundary.